Good afternoon. We are from the group number 2, and we are going to discuss about the development of the report. So in this report, we are analyzing a beam to verify if the assumptions done by this beam are correct. For this, we add weights in the right end of a beam to get with a strain gauge graphs to obtain the data to verify this. So for the theoretical introduction, we have here the graph of the beam. We have a reaction at B, and in the position A, we have the strain gauges. At the right end, we have the F force that we are applying. So the kinetic assumptions are our objective. So if our results are correct, this is going to verify that the kinematic hypothesis is correct. So next is my partner, Cos.
Now I'm going to talk about the methodology. Well, the theoretical and experimental analysis of this beam, that is an indeterminate beam, we have to follow these formulas and these rules. Here we have the shear force, the second moment of inertia, and the bending moment with the magnitudes. We're going to use the formulas of static equilibrium. Here we have more equations of the bending moment, neutral axis, second moment of inertia, inertia of complete section, normal stress, and normal stress respect to strain. And how are we going to solve this problem theoretical with these equations that I showed you here? We're going to use it. Here we have the load function, the summatory forces, the boundary conditions of the beam. We solve the problem here, evaluating in the corners, in the boundary conditions in this case, and we find the equation for the reaction in B. And with this equation, we only have to, with the, with the values that we got in the experiment, we can plot the graphics. Thank you.
Now I'm going to talk about the experimental setup, and basically the first part is focus about the beam of the geometry. For that, we identify where put the strain gate, where is the reaction, and where is the part of the when we put all the loads. And after that, we need to check the geometry and the base, the tightness, and the inches of the beam that we are going to analyze. In this case, we have a values that height of 25 millimeters and a tightness of 2 millimeters. And after that, we use the softwares. We use two softwares. In this case, is LabVIEW and EasyPlot to recover all the data. And basically, we collect the uh, electric frequency about when we have a load in the beam and how that being changed during the time when we put one load and after that one other load, and before that when we take it off all that weights. And after that, we can make a data recovery. In this case, we can see the inertial table. That inertial table we made with the initial data that we have in the beam. And after that, we can see the our best test. we can see all the loads during the time, what is the value that we obtain in the lateral strain and the top strain, and also that we make the conversion with the calibration equilibrium formula. And after that, we can compare all this data with the theoretical and experimental. And in this case, we have a very low strain error percentual. And now you can see all the pictures that we have the strain befores during all the conditions. And that's all.
Analysis of result. The experimental evaluation of the aluminum beam shown here consists with a bending theory. The relationship between the upper loads and the measured strain present a linear strain, confirming that the material remained within its elastic range according to the Hooke's law. The comparison between theoretical and experimental results showed acceptable correlation. The small discrepancies observed can be attributed to experimental factors such as calibration errors, electricity noise during data acquisition, slowing strain Gauge misalignment, and approximation made during data processing using AC plot and LabVIEW. And conclusion and recommendation. The experiment successfully demonstrated the bending behavior of a static indeterminate aluminum beam under concentrated loads. The experimental results show goes ahead with the theoretical prediction obtained for pure bending theory, validating the analytic methodology used to calculate the bending moment, strength, and deflection. For future experimental, it is recommended to improve the calibration process of the strain gauges at data aggregation system to resume measuring errors. Thank you.